another form of energy. Okay. Is there any other name for a device which converts one form of energy to another form of energy that you get confused with? Sorry? That's an example of this. There are many physical phenomena where one form of energy is converted into another form of energy. All this, generally, we can call it as transducers. Is it clear? And what is sensor? Sensor is a device which is used for measuring the physical quantity of the system, okay, of the world. Any physical quantity you wanted to measure, the device that you use for that, you call it a sensor. Give me one example of a sensor. Any sensor?
LDR.
Huh?
LDR.
LDR. Light dependent resistor. LDR. Okay. Yeah, we will finish this and then we will come. So, LDR is a sensor. We call it as a sensor. Why? We wanted to measure the light intensity and proportional to the amount of light that is falling on the LDR, the resistance changes. Then that means the light energy is converted into change in resistance. One form of energy into converted into another form of energy. When you supply current to that resistor, the electric energy that is flowing through that resistor gets changed. So you have a change in electric energy proportional to change in light. So is it a transducer? LDR, is it a transducer? What is the definition of transducer? Simply any device which converts one form of energy to another form of energy. Okay. One form of energy to another form of energy is a device. Okay. That device you call it as transducer. When you call a transducer as a sensor, you call that as a sensor when it is the transformation of one energy to another energy is used for measuring a physical quantity in the body. Okay. So here LDR, he calls it as a sensor because we measure change in current because there is a change in resistance. That change in resistance comes because of change in the light intensity falling on it. Okay. Basically we are measuring the light intensity on the environment using that LDR, so we call that LDR as a sensor. Is it understandable? Yes? So sensor is a device used for sensing, measuring, quantifying a physical quantity. Transducer is a device, any device, simply converts one form of energy to another form of energy. Is it okay? Alright? Then, what is the difference between a machine and a transducer? Okay, so here comes the difference between a signal and energy. Okay, there is something called signal, there is something called energy. Right now I said one form of energy to another form of energy. It's not very precise. I want to be very precise out there. What is the difference between just saying energy and signal? I'll elaborate on that. Suppose I have some eye problem. So my eyes keep on blinking like this. My eyes keep on blinking like this. That is simply energy. Okay, that's simply energy. It doesn't convey any meaning to anyone. Okay. Whereas my eye does not have any problem, but then simply I say, you understand something from the communication. The action is same. What is the action? Blinking of eye. But when I do like this because of my illness, it doesn't convey any meaning. Maybe doctors understand it as a meaning, or you have certain illness. But other than that, the general public doesn't understand anything out of that. And you call that as simply energy. One form of energy to another form of energy. There is no signal. Okay. Signal means it should have some information in it. Yeah. You belong to this class? So one form of signal to another form of signal, you call it as transducer. To be very precise, it's not one form of energy to another form of energy. For example, even fan, we will not call it as a transducer. Why? It doesn't convey any meaning. It converts electrical energy to mechanical energy, but we will not call fan as a transducer. We call fan as a machine. Okay, fan as a machine. When it conveys certain information, then only you call, then only the energy becomes signal. Energy becomes signal. Okay. So anything transforming from one state to another state without any information in it, it's called energy. Either electrical to mechanical, mechanical to thermal, or whatever. All kind of transformations or energy transformations. Okay. When you attach some signal to it, for example, if you see a sinusoidal waveform in a CRO, the Tamil Nadu Electricity Board current, if you take and see TNB current in CRO, you will see a 50 Hz signal. 50 Hz signal. You will see a sine wave. It's a standard AC current. It doesn't have any meaning. It doesn't have any meaning. Whereas, if you connect a sensor and the output you connect it to CRO and then see, there also you will see an upgoing signal, downcoming signal and all that. There, the upgoing indicates, let us say if sensor is a thermal sensor and measuring temperature, if the voltage goes up, that means the temperature is going up, because of that the voltage is going up. So voltage going up has a specific meaning in this particular case. Okay. So here also voltage only. Voltage is going up. When voltage is going up, it conveys an amount of meaning to you that the temperature is going up. It conveys that meaning. So you call this as a signal. You don't call it as energy. Whereas Tamil Nadu Electricity Board or Kerala Electricity Board, whatever, the electricity board current in India, it's a 50 Hz current that we get. They don't convey any information. Always it is standard 50 Hz. It doesn't carry any meaning along with it. It transfers only energy. Because it is alternating, it is going up and down. So there also the voltage only. Voltage is going up, coming down. It does not have any meaning, so it is energy. So you understand the difference between energy and the signal? Okay, so energy without information, with information, you call it as signal. Okay, so simply morning people do yoga on the terrace. This is energy. From boys hostel to girls hostel, somebody is doing it. The same action only, but that is signal. Because it conveys that meaning to the other party. So anything with information you call it as signal. Anything without information you call it as energy. Okay. So the device which converts one form of energy to another form of energy, you call it as machine. A device which converts one form of signal to another form of signal, you call it as transducer. If that transducer is used for measuring a physical variable, you call it as a sensor. Is it okay? Any questions? So three things we distinguish: machine, transducer, sensor. Okay. Machine, transducer, and sensor. Any questions? Do you have any confusions or it's clear, right? Clear, right? Fine. So that is the 2 words in your syllabus. So 2 words in your syllabus is over in the first unit. Next, as per syllabus, actually we have to learn characteristics of an instrument. So static characteristics and dynamic characteristics. Is it very sorry?
Necessary that a sensor be a transducer?
Mostly it is, because any physical parameter that you measure, only after transduction you get to read.
Rule and scale.
Yeah.
It's a sensor, but it's not a transducer.
Yeah. You actually make a comparison and then you take a signal. The scale is not a sensor; it's a device. Scale is a device. Okay.
It measures something.
it measures something. A sensor, by definition, it converts one physical quantity into another physical quantity for the purpose of measurement. Only you call it a sensor. That is your colloquial language that you learn. Scale is a sensor. Scale is not a sensor. It's a measuring instrument, but not a sensor. Sensor means it should satisfy this definition. You understand?
So can a microphone be considered a transducer?
Yes.
So when it converts the same kind of energy,
It
so it just amplifies the sound.
okay.
So can it be considered a transducer?
Naturally, it is a transducer because the pressure waves, the sound signals, the pressure waves are converted into electrical energy in the microphone. So it is a transducer. Can we call it as a sensor? Yes, you can call it as a sensor when you measure the sound intensity using that voltage, you calibrate it and then say, now I am talking in so much decibels, you talked in so much decibels. If you are able to calibrate and then make measurements out of it, you call the same microphone as a sensor. You don't make measurements, but then use it in a mic or in a phone. You talk, still it is a transducer.
So what about something like a megaphone, sir, which simply amplifies the sound?
Mega?
Like a megaphone, sir.
Megaphone. It's a transducer. Yeah, you have a loudspeaker, for example. It converts one form of signal to another form of signal. It is not a machine. It is not a machine. Loudspeaker is a transducer, which transduces the electrical signal into pressure waves. Electrical signal, pressure signal. When loudspeaker operates, you hear either a music or some talk or something. That means there is information in it. That means it is a signal, right? It's not energy. Okay, it is a signal, and one form to another form. But you don't measure anything out of loudspeaker's activity. Let's say listening to a song, you don't measure anything. Then it is a transducer. Okay. Any other questions? Okay, done. Okay. Next topic is the characteristics of instruments. Before going to the characteristics of instruments, today we would like to see why we should learn instrumentation or why we should measure measurements as an engineer. What is the need for that? Okay, that we need to learn. What is measurement? Measurement is an activity. Okay. If you can express what you are talking about in terms of some numbers, then you know something about it. This is a famous statement by Lord Kelvin. It's a famous statement by Lord Kelvin. That means you should be able to tell it in some numbers, not talking some description. See, I went and saw a big hill. How big it is? For somebody, big hill means 100 meters high. For some people, a big hill means 3000 meters high. So, Lord Kelvin says, if you can express in numbers, okay, what you are talking about, then you know something about it. Okay, measurement is all about finding that number. Okay, so we want to describe the world as an engineer, and when I say something, you should perceive the same thing. When I say 5 meter height, I'm conveying the height of some object. I and you should have same perception. For this only, this measurement comes into picture. So measurement is basically finding that number to describe the world. Okay, what is that number? Depends upon the individual physical parameter that we are interested in. Temperature, we have some numbers to say 50 degrees Celsius, 60 degrees Celsius, 40 degrees Celsius is a number. So degree Celsius is unit. That number is describing the quantity. Okay. So finding out that number. That number is actually a numerical multiple of the unit. The number is numerical multiplier of that unit. Then comes what is meant by unit. You understand what is meant by measurement? Measurement is an act of finding numerical multiplier of a given unit. Right? Measurement is an act of finding the numerical multiplier of that unit. Then what is unit? Unit is a commonly agreed standard quantity is unit. For example, we want to describe length. Okay, we want to describe length. In olden days, the unit system started like this. I wanted to sell the tied flowers, the flower rings I want to sell in terms of length. Okay. How they sell it? In some length units they have to sell. Okay. So we all agreed. Okay? Let's say we are all belong to one country and we all sit together and then come to a common consensus. We say hereafter 1 feet or 1 feet or one length means from here to here. Okay, this is basic unit hereafter. This is the basic unit hereafter. Okay, hereafter I will express always in terms of this. Let's say this is 1 feet because leg I cannot show. So this is the hand. Let's say this is feet. Okay, so this is 1 feet hereafter. Any measurement we will express in feet hereafter only based on this. But for me it will be little longer, for somebody it will be little shorter, for somebody else it will be still longer. So there is no standard for this. So earlier days what people thought that country king's foot length is taken as 1 foot, 1 length, basic length. So they all standardized that. When that king dies, new king comes, the new king's size may be different. So everything has to be changed. They thought no, this is not very better standard that we can have. And this is not okay with it. So they thought of establishing some unit which is reproducible, which is not depending on anybody or any factor for that matter. Independent of everything, independent of temperature, location, height, human, all that, and it should be reproducible in the place that you want to reproduce. Okay. Then only this becomes standard unit. Okay, so they started finding the standard way of defining units. You understand what is meant by unit? Unit is commonly agreed standard unit quantity. Hereafter this will be 1 feet is unit. How much is the length of this? I measure so many times. Oh, this is 20 feet. This is 20 feet. That means what? Like this, 20 times length is there. That is the meaning that we convey. That 20 is the numerical multiplier of this unit. That 20 is the numerical multiplier. The act of measurement, we find out that numerical multiplier. That 20 is found out by the act of measurement. Okay, so measurement is finding the numerical multiplier n, and m is the unit. Okay, so now we understand two terms. One is measurement. What is measurement? Okay, and the other one is unit. Okay, and attached to unit there is something called standards, and we will not go to standards at this class. Maybe next class we will talk about standards. It's a huge topic. Why measurement? Why we should measure? Day-to-day activity itself we do a lot of measurements. Starting from, we just wanted to know certain quantity or certain quality. So we do measurement. Okay. Like morning, we want to know what is the time. So we have a device for measuring time and measure time. We want to know the density of milk when the milkman comes in the morning. If child is having fever, we want to know what is the temperature of the kid. All that we wanted to know what is that parameter, either the density of the milk or temperature or time. We want to know. Okay? That's one reason, just for knowing purpose. Another, we wanted to control. What is that we want to control? We want to monitor certain things. We want to control certain things. Control means what? The bread toaster is there. Okay, bread toaster. We want to know what is the temperature because we want to control the temperature. There, it's not that I simply wanted to know the temperature. I want to know and control the temperature. For the purpose of controlling, I wanted to know the temperature. Why? If bread toaster temperature goes very high, the bread will be overburned. So it's not eatable. So you have to throw it out. It becomes waste. And also size. Why people take measurement for stitching? That's because they have to make dress for our size. Something like that. So the bike and cars, we have speedometers because we want to control the speed. And then here is physical verification, right? your physics master comes and says density is mass per unit volume. Mass per unit volume. There is a fundamental definition of density. And for density of water, they say, what is the density of water? 1000 kilogram per meter cube. Okay, that your physics master comes to the class and then says, you wanted to question, sir, how do I believe that you are telling some number? How do I believe? If you want to verify, you take a container of 1 meter by 1 meter with the depth 1 meter, pour water, and then weigh it in a weighing bridge. It will be 1000 kilogram. So if you want to verify already established physical quantity, you have to go for measurement. Some of the laws people have used equations. Engineering mechanics you might have learned. V square is equal to U square plus 2GS. And while teaching this, your professor would have also taught, if you know the direction and initial velocity, and if the stone is vertically thrown, it's not direction. Vertical means it's always 90 degrees. So 90 degrees vertically if you throw a stone. You tell me your initial velocity, I will tell you how far the stone will reach. No, you say, sir, come on, sir, don't bluff like this. No, it's not possible to predict. Suppose you have a doubt and you want to establish you want to measure and verify. Then you should have some mechanism to measure the initial velocity. Also, you need to have some mechanism to measure the height the ball has reached. Okay, and then you substitute this formula, you will be able to identify. So, any empirical equation, the equation that you have already established, you want to verify, you need to go for measurements. And then you come for strength of material law. Okay, and what is Hooke's law? Stress is directly proportional to strain within elastic limits. Okay. There is no use of that law if there is no measurements. Because there is measurement, within elastic limit, you increase the stress and find out corresponding strain, and then from that you find out something called Young's modulus, isn't it? You find out something called Young's modulus. That's the property of a particular material. For each material, it will be different. And once you have that, then you will be able to use it for many design calculations. I have so much of load, Young's modulus is this, so what will be the strain? You are able to do that using data book because some people have done instrumentation already, used measurements, and established this. The law or the principle is stress is directly proportional to strain is useful only because of measurement. If measurement is not there, that will be simply a statement. You can read and enjoy and then go. You cannot apply it in engineering. If you want to apply it in engineering, you need to go for instrument. And then this is of course Fleischmann mechanism. This is called mechanical integrator. This is called mechanical integrator. How many of you know the Fleischmann mechanism? When the flyball, this is a shaft, there are two balls. This is a sleeve. This sleeve can move up and down, whereas this sleeve cannot move, that is fixed. Between the fixed sleeve and moving sleeve, there is a spring. There is a spring. As the ball rotates, the balls will try to move up. You are able to understand? That's because of centrifugal force. So when the rotation speed comes down, it will come down. When rotational speed increases, it will try to go up. It will not go above this, it will go up to this. Okay, so when highest speed, it will reach here. So the sleeve also moves up. So at any point of time, the sleeve will give the instantaneous velocity, the rotational velocity. If the speed is high, it will be high. So that you can measure if you put a scale and a pointer here. So instantaneous velocity. Okay. And then here you have two bevel gears connected to a mechanical counter and count the number of rotations that it has made. Okay. So number of rotations you will get here, instantaneous velocity you will get here. You have a basic relation v dt. Integral v dt is x. X is integral v dt, where x is the displacement, v is the velocity. Okay, if you integrate velocity, you will get displacement for given time duration t1 to t2. I think these are all fundamentals, you know it, right? Fine. Now, what I do, I have a rotating fly ball. I start the stopwatch at T1, reset the counter to 0, leave the stopwatch and the counter at the same time. Now the fly ball is rotating, counter is counting, and at T2 I stop my counter as well as time at the same time. Now I will have every time instantaneously I know the velocity here, but that's not very important here. I'll link it to velocity in a short while. Here you have the integration value. Integration means what? What is in words? What is integration? Summation, continuous addition, summation. Okay. So how many rotations the shaft has rotated is the integrated value from time t1 to time t2. The velocity may be uniform, may be varying from low, high, in any form. Whatever is the total number of rotations it has made so far, these integration values that you get here. Whereas the instantaneous velocity you will get here. Alright? Is that clear? Right. Now, sir, what is the linkage of this to measurements? Okay. There are some mathematical equations for which the integration is not possible. Direct integration is not possible. So if you have such a complex expression, that expression you link it to your velocity of rotation. That expression you link it to the velocity of expression. And then this reading will give you the integration value from T1 to T2. Integral T1 to T2, the integration value you will get that. So this method in olden days people have used as integration by analogy. Integration by analogy. They don't use actual mathematical functions. The mathematical function is converted into proportional voltage to the motor, which rotates this shaft and take this as a proportional value. This is the olden way of integrating where the electronic integrators were not there. Recently means over 100 years back, people have found integrators, electronic integrators. So we have capacitor and associated circuits for integrating devices we have. So we use them to integrate any complex function. Because of that we don't use it. Otherwise, mechanical integrators only people were using where direct integration was not possible. By formula, if it is not possible, they use it. And measurement is the input for most of the control systems. Any control system you want to use, the input comes from the control system. To sum up, these are all the reasons why we should go for measurement. One, to monitor the process, to know the process basically, to control the process and operation, determine the material properties, practical verification of already established quantities and constants, validate the theoretical predictions like the stone which we have thrown it up, from empirical relationship, form empirical relationship. What is meant by empirical relationship? Huh? Based on? Yeah, where there is if the expression or the equation is not derived from first principles, you conduct set of experiments, from the data you derive the expression, that expression you call it as empirical relation. Okay, for that measurements is useful. To provide solution to the mathematical equations by means of analogy and to give input to computer based measurements so that you will be able to make measurements. So these are all the reasons why we go for measurement. Any questions? That's a general reason why one should go for measurement. Sir, I am an engineer. Why I should go for? Why I have to go for measurement? Only one reason. Engineers deal with basically three things: material, energy, signal. Material, energy, and signal. Engineers every day deal with this. Okay. Now, I think I am going to put that slide. It doesn't matter. You take injection molding machine. You know what is meant by injection molding machine? You have plastic beads, small plastic beads, like tablets, plastic tablets. Sorry. From hopper, it goes to a heater. In the heater, it gets heated up, comes as a paste through a die. Small hole, it comes out. That is sent to a die upon pressure, and it forms the shape of the die inside. it involves three things: energy, material, and signal. What is the energy there? It is the heat energy. The electric coils will be there that will heat the beads, make it into paste, plastic paste. So that comes out as a paste. It should be in a particular viscosity. Then only it will smoothly flow and get dry. If it is too liquidous, viscosity is less, it simply get wasted. Even from changing from one dye to another dye, it keeps flowing. We don't want unnecessarily flow. The paste, the plastic paste should flow only when we apply pressure to push it into the dye. Rest of the time it should remain there. If the viscosity is very high, it is very difficult to push into the dye, and before completely filling it, the plastic will solidify and we cannot make the shape that we want to make. Okay, so maintaining exact temperature is very important. So that is the signal there. Okay, that is the signal there. So material is the plastic beads, the energy is the heat energy that we supply, and the signal is the exact temperature that you have to maintain. Okay, it's not the temperature, just temperature, heat energy is the energy. Let's say 340 degrees Celsius if you maintain, that injection molding machine will work for example. If it goes to 350, lot of material will be wasted. If it is maintained at 240 or 340, 320, lower temperature, you will not get plastic parts completely filled. You will get pieces with defects. Okay, so your material will be wasted. Whatever the energy you have used for heating the material, that heat energy, current bill you will pay unnecessarily. Once the signal is lost, your material is lost, your energy is lost. Because of that, for engineers it is very important to have great control over the signal. In engineering systems, the signal you should have control. Instrumentation and control is all about learning more about how to acquire that signal, how to control that signal. Because of that, it's very important. Is that clear? Any questions? Okay, we'll stop here. Next class we will stop.